So we've been looking at proving identities, and there's certain tricks that we saw or talked about that you can do in order to help you prove these identities. And as we go through and look at some more examples, I'll reiterate what I had said in the other video of things that we can do in order to help us show these identities. And so again, when we're looking at an identity to show, we're choosing one side of the identity to work with and just working with that side and getting that side to look like the side that we did not work with. So you're not moving things to each side of the equation you're only doing that when we're solving equations, but proving or showing an identity holds true, you're looking at one side. And that one side that you choose usually looks like the more complicated side. So let's look at some examples. So the first example we have in front of us is sine u times cosecant u minus cosine squared u equals sine squared u. So the left-hand side definitely looks more difficult. So that's the side I'm going to choose to work with. And I'm just going to put LS for left side. So working with the left-hand side, I want to manipulate that to look like sine squared u. So one way that we can start this is rewriting everything in terms of sines and cosines. So that sometimes is something that's helpful. And so if we write this left-hand side in terms of sine and cosine, the only thing I need to rewrite is cosecant u. And cosecant u is the same thing as 1 over sine u minus cosine squared u. So notice after we rewrote cosecant u in terms of its reciprocal function, 1 over sine u, we now can cancel the sine u times 1 over sine u, the sine u's cancel, leaving us with 1. So 1 minus cosine squared u. So I'm seeing this and it looks similar to my Pythagorean identity. So recall our Pythagorean identity was cosine squared, let's just use the u since ours have it u in here, plus cosine squared u plus sine squared u is equal to 1. And so if we subtracted cosine squared u on both sides of the equation, notice that we get sine squared u is equal to 1 minus cosine squared u, which is exactly what we have over here. So 1 minus cosine squared u is equal to sine squared u. So we showed that the left-hand side was equal to the right-hand side. And so we showed that identity was true. And then that little box says that we did what we wanted to do and we showed that proof. So the next example in front of us, we have cosecant theta minus 1 times cosecant theta plus 1, and that's equal to cotangent squared theta. So notice I have a difference of squares in here. So if I multiply this out, so this is in the form of a minus b times a plus b, which is the factored form of a squared minus b squared. So if I go in here and I square my cosecant theta minus, and I square my 1, so I'm working on the left side. This gives me cosecant squared theta minus 1. So this looks like probably the Pythagorean identity. So let's, and I don't have that one memorized, but I talked to you guys about how you can derive it really fast. So using the one we just did above, cosine squared theta plus sine squared theta equal 1. We can derive the other two by either dividing every term by cosine squared theta or dividing every term by sine squared theta. Well, I have a cosecant squared theta in here. And so I know cosecant squared is 1 over sine. So I'm going to start by dividing everything through on this by sine squared. Just doing some side work over here. So cosine squared theta all over sine squared theta, that's cotangent squared theta, plus 1 equals 1 over sine squared theta, that's cosecant squared theta. So I'm trying to make my left-hand side cosecant squared theta right now minus 1 equal cotangent squared theta. So notice here, if I subtract 1 on both sides, I see that I get what I want. Cotangent squared theta equals cosecant squared theta minus 1. So I'm just going to rewrite this left-hand side using that. This is the same thing as cotangent squared theta, which I wanted to show. Okay, so we have secant u minus tangent u all over cosine u, and not all over. Sorry, let's start that over. So this example says secant u minus tan u equals cosine u all over 1 plus sine u. So I need to choose which side I'm going to work with. This one, they both kind of look complicated. I'm thinking working with the left-hand side again. So let's rewrite secant u and tangent u in terms of sine and cosine. And so secant u is the same thing as 1 over cosine u minus tangent u, which is sine u over cosine u. So rewriting those as their quotient identities, we can look at, we have the same denominator, so we can rewrite this as a single fraction. So 1 minus sine u all over cosine u. So it looks like it doesn't look anything like what I have on the other side. But one trick to do, if things aren't falling out, is to multiply by the conjugate of either the numerator or denominator. So in this case, let's multiply by a fancy 1 and the conjugate of 1 minus sine u. And so remember, the conjugate is just changing the sign between those two terms. So that would be 1 plus sine u all over 1 plus sine u. So doing that, our numerator now is 1 minus sine u times 1 plus sine u. That's a difference of squares. So if I just square the first term, that's 1 squared minus squaring the second term, which is sine squared u all over. I'm not going to distribute for the piece that is not multiplied by the conjugate. So I'm going to keep that as factor form, cosine u all times 1 plus sine u. By doing that, notice that this 1 minus sine squared u, this is part of that Pythagorean identity. One minus sine squared u is the same thing as cosine squared u all over cosine u 1 plus sine u. So I have a factor of cosine u both in the numerator and denominator. So cosine u goes into cosine squared u once, leaving us with just cosine u all over cosine u goes into itself once, 1 plus sine u, which is exactly what we needed to show. Okay, so looking at our next example, 1 minus, and then we have the term cosine squared theta. That cosine squared theta is over 1 plus sine theta. That is equal to sine theta. So I know I'm going to work with my left-hand side. And sometimes you don't know where to start. I first thought, okay, let's just get a common denominator and rewrite that as one fraction. But then looking at that, I would have a 1 plus sine theta minus cosine squared theta, which I don't think is going to help me. So actually that could help me. And the other thing I could have done though is multiply by that conjugate 1 minus sine theta to that second fraction. So I'm not sure exactly which way I want to go. I think both ways will probably help me and get there. So let me go with what I first originally thought. So let's rewrite this one with a common denominator so that we can add it to that fraction. And so I can rewrite that one as 1 plus sine theta all over 1 plus sine theta. And then we would have minus, so let's just put it over one fraction, minus this cosine squared theta. So looking at this, let's rewrite this. It looks like I have a trinomial. It's quadratic, but I have sine and cosine in that numerator. So if I go back and use the fact again, that cosine squared theta, that's the same thing as 1 minus sine squared theta. So let's use that fact and rewrite our cosine squared theta. So we would have 1 plus sine theta minus, we need parentheses, the quotient minus parentheses 1 minus sine squared theta all over 1 plus sine theta. So distributing my negative, and I'm going to rewrite it in descending order of power. So this would be positive sine squared. This right here gives me -1, but let me just write plus sine theta first. So this would be -1, and then we have this +1 here, all over 1 plus sine theta. So those ones cancel. So -1 plus 1, that goes away. And so now I notice that my numerator, I can factor out a single sine theta. And so factoring out a sine theta, I get sine theta plus 1. And then I have my denominator 1 plus sine theta. Well, 1 plus sine theta is the same thing as sine theta plus 1. So those simplify, cancel out, just leaving you with the sine theta, which we wanted to show. So our next example has cosine theta all over 1 minus tangent theta plus sine theta all over 1 minus cotangent theta. We want to show that that is equal to sine theta minus cosine theta. So again, looking at this, my left-hand side is looking like the most difficult side. So there's a couple ways I can approach this. I could get a common denominator and rewrite that as a single fraction. I'm also noticing that I could rewrite things in terms of all sines and cosines. I think I want to go that route. So let's rewrite the following. So we have cosine theta all over 1 minus, well, tangent theta we can rewrite as sine theta over cosine theta. Plus I have sine theta all over 1 minus cotangent theta, but cotangent theta is the same as cosine theta all over sine theta. So now that I've rewritten this all in terms of sines and cosines, I now have this complex fraction. So I have fractions within a fraction. So let's get rid of it so we don't have a complex fraction anymore. And so there's a couple ways to do this. I tend to like to multiply by a fancy one to clear the fractions within the fractions. And so if I look at my first fraction here, the only thing that I have a fraction within that fraction is that sine theta over cosine theta. So if I multiply this by a fancy one, cosine theta over cosine theta, and when I distribute on the denominator, that cosine theta would fall out in that denominator and we wouldn't have a complex fraction anymore. And wanting to do the same kind of reasoning with that second fraction, this expression, I want to multiply by a fancy one so that this fraction within the fraction goes away. So looking at the denominator, it's sine theta. So I'm going to multiply both the top and the bottom by sine theta. So doing that, I have cosine theta times cosine theta is cosine squared theta. All over, distributing my cosine theta times the 1 is cosine theta. Distributing my cosine theta times this sine theta over cosine theta. The cosine thetas cancel, leaving us with minus sine theta. Plus, so sine theta times sine theta, this is sine squared theta. All over, distributing our sine theta times 1, we have sine theta. And then sine theta times cosine theta over sine theta. Sine theta does cancel, leaving us minus cosine theta. So almost have common denominators. We're just off by the sign. So if I factor out a -1 from one of those denominators, let's just do it from the second one. We would have a common denominator. So pulling out a -1, this would now be negative sine theta plus cosine theta. So I'm going to pull my negative. I can pull this out front. So rewriting this, I have this cosine squared theta all over my common denominator, which is cosine theta minus sine theta. And now we have this, it's now minus sine squared theta. So notice cosine squared theta minus sine squared theta in that numerator, that's a difference of squares. And so we can factor those difference of squares. This is the same thing as cosine theta minus sine theta, all times cosine theta plus sine theta. All over cosine theta minus sine theta. So cosine theta minus sine thetas cancel. And we're left with cosine theta plus sine theta. Which is what we wanted to show. So our next example, tangent x minus cotangent x all over tangent x plus cotangent x. And then plus 1 is equal to 2 sine squared x. So working with my left side. Not sure how I want to approach this one. Let's start with, again, rewriting our tangents and cotangents in terms of sines and cosines. So tangent x I know is sine x over cosine x. minus cotangent x, and that's cosine x all over sine x. That's all divided by tangent x, which is sine x over cosine x. Plus cotangent x, which is cosine x over sine x. Plus 1. So we want to get rid of our fractions within the fractions. I notice that I have a cosine x in a denominator and I have a sine x in a denominator. And so you want to look for the least common denominator. And the least common denominator is cosine x sine x. So cosine x times sine x all over 1 divided by cosine x sine x, which is also divided by 1. So now that when we distribute this, our fractions are going to go away. So cosine x sine x times that sine x over cosine x, the cosine x cancels, leaving you with sine x times sine x, which is sine squared x. Minus, and then when we distribute it to the second term in that numerator, our sine x would cancel, leaving us with cosine x times cosine x, which is cosine squared x, all divided by, so now distributing in that denominator. So cosine x sine x times sine x over cosine x cancels, leaving you with sine squared x. Plus, and now distributing it to that second fraction in the denominator, the sine x cancels, leaving you with cosine x times cosine x, which is cosine squared x plus 1. So notice that sine squared x plus cosine squared x is our Pythagorean identity. Cosine squared x plus sine squared x is equal to 1. So we can rewrite our denominator there as 1. So we have sine squared x minus cosine squared x all over 1. So I really don't have to put over that 1 plus 1. So I'm trying to get this, manipulate this to look like 2 sine squared x. And so let's go back to that Pythagorean identity and let's rewrite cosine squared x in terms of sine. And so cosine squared x, recall, if we isolated it on that one side, would be 1 minus sine squared x. So let's go in there and replace this cosine squared x with that. And so we have sine squared x minus parentheses 1 minus sine squared x and our parentheses plus 1. So distributing our negative inside the parentheses, we're left with sine squared x minus 1 plus sine squared x plus 1. So our 1's are canceling with one another. And we have like terms. We have a sine squared x plus a sine squared x. And so that's 2 sine squared x, which we wanted to show. So the next example, we're trying to show that sine alpha plus cosine beta quantity squared plus the quantity cosine beta plus sine alpha, that quantity times the quantity cosine beta minus sine alpha. That is equal to 2 cosine beta all times sine alpha plus cosine beta. So it looks like the left-hand side is more difficult. So I'm going to work with the left-hand side. And I would probably start distributing things out and seeing if I have like terms that I can combine. So be careful because there's addition in between these two terms. We have to distribute out sine alpha plus cosine beta all times sine alpha plus cosine beta. So we're going to distribute that plus, so cosine beta times cosine beta, this is a cosine squared beta. Cosine beta times negative sine alpha, so this is minus cosine beta sine alpha. I could have just noticed that this was a difference of squares, but since I started doing this, let me just continue. So sine alpha times cosine beta, so this is plus cosine beta sine alpha. And sine alpha times negative sine alpha, so this is minus sine squared alpha. So let's combine like terms and let's distribute these two. So sine alpha times sine alpha, that's sine squared alpha. Here's sine alpha times cosine beta, so plus sine alpha cosine beta. Cosine beta times sine alpha, so plus sine alpha cosine beta. And cosine beta times cosine beta, so plus cosine squared beta. Then we have this plus cosine squared beta, so let's just write this down here. I notice that my minus cosine beta sine alpha plus cosine beta sine alpha, those cancel with one another. And then bringing down my last term of minus sine squared alpha. So I notice I have like terms in here. I have this sine squared alpha minus a sine squared alpha. So those are going away. I have this sine alpha cosine beta plus sine alpha cosine beta. There's two of those. So 2 sine alpha cosine beta. Plus, and then I have another like term. I have cosine squared beta plus cosine squared beta. So that's plus 2 cosine squared beta. So I look at what I'm wanting to show. I want to show that this is equal to 2 cosine beta times sine alpha plus cosine beta. So looking at what I'm down to, I notice I can factor out a 2 cosine beta from both of those terms. And if I do that, I'm left with the sine alpha for the first grouping plus 1 cosine beta for the second grouping, which is exactly what I wanted to show. Okay, so the next example in front of us is 1 plus cosine theta plus sine theta all over 1 plus cosine theta minus sine theta. This is equal to secant theta plus tangent theta. So they both look difficult, and I'm not sure how I would manipulate this left-hand side. So maybe let's start this time. Let's work with our right-hand side. And let's start by rewriting our right-hand side in terms of sines and cosines. So I notice that secant theta, that could be rewritten as 1 over cosine theta. Plus tangent theta, that's the same thing as sine theta over cosine theta. We have a common denominator when we do that, and that is 1 plus sine theta all over common denominator of cosine theta. It's not looking like our left-hand side. So let's look at multiplying by the conjugate of our numerator. So our conjugate of our numerator, 1 plus sine theta, that would be 1 minus sine theta. So we're going to multiply by a fancy 1. So divided by 1 minus sine theta. So if we distribute in our numerator, that's a difference of squares. So this gives us 1 minus sine squared theta all over cosine theta all times 1 minus sine theta. You notice 1 minus sine squared theta, that's the same thing as cosine squared theta. But I don't think that that's going to help me make that look like the following. So I'm kind of glad that this one is making me struggle because the other ones just kind of came out really fast. And while I was going, they kind of fell out. This one's not falling out how I want it to look. And so when you're doing these, you want to keep in mind what you're trying to make that one side look like. So I'm thinking and looking back over here. Let's go back and maybe let's work with the left-hand side instead. If I regroup the left-hand side, let's see. So I'm going to erase this. And I'm going to start over and I'm going to now work with my my left-hand side instead. So if I regroup that, maybe we can multiply by the conjugate of either the numerator or denominator. I'm wondering which one would be better. Well, let's multiply by the conjugate of the denominator. So that would be 1 plus cosine theta, in parentheses, plus sine theta. 1 plus cosine theta, that quantity. Plus sine theta. Okay, so just going to leave it in factored form on top for now. So this is 1 plus cosine theta plus sine theta all times 1 plus cosine theta plus sine theta. So that's the same thing as quantity squared here. All over. So if we distribute in the denominator, that's going to give us a 1 plus cosine theta quantity squared minus sine squared theta. Yeah, this one's not coming out like I want it to. I know the sine squared could be rewritten in terms of cosine and sine. I can distribute in the numerator. If I did that, that would be like 1 plus cosine theta times 1 plus cosine theta is 1 plus cosine theta quantity squared. Plus I would have 2 sine theta all times the quantity 1 plus cosine theta plus sine squared theta all over. And if I distribute in the numerator, I get 1 plus 2 cosine theta plus cosine squared theta minus sine squared theta. So maybe let's distribute up here in the numerator. And so if I FOILed out 1 plus cosine theta times 1 plus cosine theta, I get the same thing I had down here. So 1 plus 2 cosine theta plus cosine squared theta plus 2 sine theta plus 2 sine theta cosine theta plus sine squared theta all over 1 plus 2 cosine theta plus cosine squared theta minus sine squared theta. So I'm thinking that if we regroup things, we know that cosine squared plus sine squared is 1. Maybe rewriting cosine squared in terms of sine squared in the denominator. So maybe let's regroup things and rewrite things. So here so far I have 1 minus 2 cosine theta plus 2 sine theta cosine theta. Oops, noops. 2 sine theta plus 2 sine theta cosine theta. Plus cosine squared theta plus sine squared theta all over 1 plus 2 cosine theta. I'm going to want a sign in the bottom, so I'm going to use the fact that this cosine squared is the same thing as 1 minus sine squared. So maybe let's try that. So plus one minus sine squared theta. It's just that cosine squared theta. And then we have a minus sine squared theta. So I noticed that this cosine squared theta plus sine squared theta, that right there is equal to 1. So let's regroup things doing that. So I would have this 1 out front here in the numerator plus this 1. So that gives me 2. So this is 2. Oh, yay. I also noticed, I didn't notice that before, but we had this negative 2. Oh, no. I thought that was multiplied. We don't. Let's just bring it down. So we have minus 2 cosine theta plus 2 sine theta minus 2 cosine theta plus 2 sine theta plus 2 sine theta cosine theta. all over. So let's combine like terms. We have this 1 here plus this 1 here, that's 2. So plus 2. Plus 2 cosine theta. Minus 2 sine squared theta. I need that to look like secant theta plus tangent theta. And I'm wondering if I should have, and I wasn't thinking right. Let's go back. I'm thinking that if I turn that sine squared into a cosine squared, we might be able to factor. I notice I can factor out a 2 on top and a 2 on the bottom, and those would cancel. So let's just pull out a 2 on top. So that is all times 1 minus cosine theta, sine theta, sine theta, cosine theta. All over 2. That would be 1 plus cosine theta minus sine squared theta. So our 2's cancel. This sine squared theta, this is the same thing as 1 minus cosine squared theta. So if we distributed that negative there, so 1 minus cosine theta. I'm also noticing if I factored out this sine theta here, if I factor out a negative, let's factor out a negative sine theta from those 2 terms. Oh no. I was thinking that it would give me the same thing. It doesn't. So that would give me 1, just factoring out a positive sine theta, 1 plus cosine theta. All over. So distributing my negative 1, that would cancel with this 1 here. That would give me a cosine squared theta plus cosine theta. It's not falling out like I want it to. Let me pause for a second and let me look into this, and I'll come back and tell you. So just a sec. Okay, so we took a break and I went back and looked at my work and noticed that I made an error here. I kind of put a star by it. But when I distribute out 1 plus cosine theta quantity squared, I put a minus here, which that should have been a 1 plus 2 cosine theta when you distribute that out. And so if we go back, all I need to do is rewrite that minus 2 cosine theta as plus 2 cosine theta. So let's just go in there and put plus in all those spots. So notice I have a 1 plus cosine theta I'm going to put parentheses around there, plus sine theta all times that quantity, 1 plus cosine theta. And so I can factor out in that numerator a 1 plus cosine theta. If I factor out 1 plus cosine theta, we're left with 1 here plus sine theta. All over. So let's factor out a cosine theta in the denominator. If I factor out a cosine theta in the denominator, I'm left with cosine theta plus 1. Well, 1 plus cosine theta and cosine theta plus 1, those are the same things, and those are going to simplify. So we're left with 1 plus sine theta all over cosine theta. Let's rewrite that as a single fraction, or it actually has 2 single fractions, sum of 2 fractions. So 1 cosine theta plus sine theta over cosine theta. But 1 over cosine theta is secant theta plus sine theta over cosine theta, which is tangent theta. Which is where I was trying to get to. So we finished that proof. Okay, so I'm going to stop there today. So you're having an exam a week from today. That's going to cover chapter 7, chapter 8.1 through 8.4. At the beginning of class, I made a separate video on directions on some assignments I want you to do to help you prepare for the exam next week. So make sure you watch those, that video, and do the end of the chapter tests and grade your end of the chapter tests. But you get directions through that, watching the other video, or through watching or looking at your weekly module for this week. So next week we will review on Tuesday for your test on Thursday.